Welcome to The Explainer. Today, we're diving headfirst into a literal game changer at the intersection of AI and quantum computing. We're going to unpack some dense but absolutely fascinating research that fundamentally shifts how we can use near-term quantum computers to organize really complex information. It's a big one, so let's just dive right in.
So here's the central mystery we're tackling today. Can a noisy, imperfect quantum computer perfectly map the absolute chaos of our data? I mean, imagine taking a massive, chaotic universe of high-dimensional data and trying to map it flawlessly onto a neat, low-dimensional grid using a quantum computer. Sounds awesome in theory, right? But as we know, current quantum hardware is inherently noisy. It's imperfect. The real question is, can an imperfect machine create a perfect map? Well, the answer is a resounding yes, but only if you completely change the rules of the game.
To get there, here's our roadmap. We're covering 1. Mapping the data universe. 2. The quantum noise bottleneck. 3. 3 NRQ-KSOM innovations. 4. Achieving perfect grid coverage. And finally, 5. The purity trade-off. Let's get to it. Section 1. Mapping the data universe. Let's set our baseline first by looking at the classic data organization problem. Right, so before we go quantum, we really have to understand the classical foundation here, self-organizing maps, or SOMs. Imagine a SOM as a highly organized, maybe slightly obsessive librarian. If you hand this librarian a massive, chaotic pile of books with dozens of different attributes, genre, length, author, publication year, their job is to translate all that crazy complexity onto a simple, flat 2D floor plan so you don't get lost in the stacks. That's essentially a SOM. It groups similar high-dimensional data points together on a visual grid. Now look at the stark contrast in these maps of the iris dataset. See those empty gray squares in the classical map? Those are dead zones. The classical librarian did an okay job, but they left huge chunks of the floor plan completely empty, maxing out at just 83.3% data coverage. On the right, our quantum solution utilizes exactly 100% of the grid. But wait, why couldn't we just use a standard quantum computer to fix those dead zones in the first place? Moving on to Section 2, the quantum noise bottleneck. Let's introduce our anticipated hero, quantum computing, and see exactly why it struggles here. So what if we just hand this job over to a quantum librarian? Well, we immediately hit 3 massive walls. First up, our current NISQ devices, noisy intermediate-scale quantum hardware, they're fragile. Hardware noise exponentially destroys the global state fidelity of the machine. Second, standard algorithms use fixed training schedules. They literally don't adapt to how the quantum system is actually learning, which leads to premature freezing. And third, running a full quantum circuit for every single data comparison, it takes entirely too long. Basically, our quantum librarian is easily distracted by noise, rigidly inflexible, and moves at a snail's pace. Which brings us to Section 3, 3 NRQ-KSOM innovations. Let's look at the solution. Enter researcher Itzhak and a truly remarkable paper. He came up with the Noise-Resilient Quantum Kernel self-organizing map. Yeah, it's a mouthful, so we just call it NRQ-KSOM. To fix our broken quantum librarian, Weinberg introduced 3 brilliant pillars: the projected quantum kernel, adaptive neighborhood scheduling, and feature caching. Let's break these down one by one because they're fascinating. First up is the noise armor. Standard quantum algorithms rely on full quantum state fidelity. Basically, if even a tiny part of the system gets noisy, the whole thing just degrades exponentially. You can see that represented by the n in the top equation. So Weinberg's crucial move was swapping this out for a projected quantum kernel, or PQK. Instead of looking at the fragile global state, PQK looks at localized expectation values. Notice how the n completely disappears in the bottom equation? The degradation happens locally now. This gives the algorithm an exponential resilience advantage against noise, and that advantage actually grows as you add more qubits. Innovation number 2, the adaptive schedule. Look at how that blue line, representing Weinberg's adaptive method, just plummets compared to the dotted classical method. Instead of a rigid, fixed learning schedule, NRQ-KSOM monitors the weight updates dynamically. It's kind of like a camera lens constantly adjusting its focus based on the movement in the frame. If the algorithm is exploring a lot, it widens its view. If it's stagnating, it tightens focus. This actively prevents the map from freezing up prematurely, and it reduces quantization error by a massive 27.8%. And that brings us to the third big one,
brilliantly illustrated by this massive number: feature caching. Because of how the PQK math shakes out, Weinberg realized you absolutely don't need to run the quantum circuit for every single comparison step. You can run the quantum feature extraction just once per sample upfront, cache it, and do the rest of the training classically. This drops the computational complexity from ONGE, which factors in grid size and epochs, down to just ON. For the datasets tested, that resulted in a staggering 2,500 times reduction in computational cost. Sluggish training suddenly becomes lightning fast. Section 4. Achieving perfect grid coverage. Okay, let's look at the ultimate proof of what these three innovations can actually do in practice. The visual proof here is just undeniable. In these coverage charts, the classical SOM plateaus at 92% for both the Iris and WEIN datasets, but the NRQ-KSOM, 100%. 100%. 100%. Across all three benchmark datasets, the quantum algorithm perfectly distributes the data, leaving absolutely zero dead zones on the map. But you're probably wondering, how does it hold up against actual hardware errors? Well, charting grid coverage against noise probability reveals something absolutely wild. Even as depolarizing noise gets cranked all the way up to 0.05, which, by the way, covers the full range of current superconducting hardware, that coverage line for NRQ-KSOM stays miraculously flat at 100%. The noise armor of the PKQ, it literally works in practice. And here is the incredible aha moment. How is it covering the grid perfectly? Look at the original data space. See that tight, isolated cluster? That is exactly what causes dead zones in classical maps. Now compare that to the post-transformation map. The quantum algorithm has physically unpacked and uniformly redistributed the data points across the space. It mechanically forces perfect grid coverage because it is fundamentally reshaping the geometry of the data itself. Which naturally leads us to Section 5, the purity trade-off. Perfect coverage is amazing, but we've got to introduce a necessary nuance here. Look, in data science, you rarely get something for nothing, right? There's almost always a compromise. Take the Iris dataset, for example. NRQ-KSOM boosts coverage to a perfect 100%, but notice that final column. Purity drops from a perfect 1.0 down to 0.880. Because the quantum kernel forcibly spreads the data out so uniformly to kill those dead zones, it ends up slightly blending the boundaries of classes that were originally very tightly separated. And these U matrices visually cement that exact trade-off perfectly. With the classical SOM, you get a very sharp, dark boundary band. You can clearly see the hard border between different clusters. But with the NRQ-KSOM matrix, it looks much more washed out and distributed. Those distinct, sharp borders are traded away in favor of a smoother, far more uniform utilization of the entire space. So, knowing this trade-off, when should you actually deploy this tool? Well, if your goal is highly discriminative class separation, stick to classical. But if your primary objective is maximizing output space utilization, like when you're building comprehensive code books, doing complex density estimation, or working with quantum-native data like quantum phase classification, NRQ-KSOM is the unmatched winner. It guarantees every single inch of your map is put to work, regardless of hardware noise. Which leaves us with this final thought. Weinberg's work proves that even on today's noisy quantum hardware, we can leverage quantum geometry to break through classical mapping bottlenecks. If a projected quantum kernel can completely unravel and uniformly map classical data today, just imagine what intricate, wildly complex data manifolds we're going to be able to map as this hardware evolves tomorrow. Thanks for joining me on The Explainer, and keep questioning the data universe around you.